Okay, so today we are going to look at the final type of polynomial function that we're going to study in this course. And this is a cubic function. It's called cubic. It's degree 3. Okay, so it is called a cubic function. Okay, and the standard form when everything has been expanded out of a cubic function is f of x equals ax cubed plus bx squared plus cx plus d. A would be your leading coefficient, and d is your constant. Okay, and remember, we have been sort of paying attention to those two values as we've been looking at each type of function. A can't equal 0, because if a were 0, this would go away, and then we would just have a quadratic function. Okay? So we're going to start out by sketching a couple of graphs. The first one is f of x equals x cubed. And the second one is g of x equals negative x cubed minus 4x squared minus 3x plus 3. So if you have a graphing calculator, it probably would be beneficial for you to do this with me. I just want to ask again, because I can't remember, how many people here have Casios? Just a couple. Okay. So interesting. Like, that is just totally changing. In my grade 10 classes this semester, I think more people had Casios than TIs. Either one is good. Okay. So I'll do this on both. So one of them is just y equals x cubed, x to the power 3. And the second one is, what was it? Negative x cubed minus 4x squared minus 3x plus 3. Okay. Negative x cubed. Was it minus 4x squared? I think so. Okay. Minus 3x plus 3. Okay. And I'll do that on here as well. Okay, so I'm going to go to graph, and I'll just delete that. And I'm going to put in x cubed, and I'm going to put in negative x cubed. Whoops, sorry. Get rid of that. And then minus 4x squared minus 3x. Oh, wait, shoot. Okay, right. So once you're done with an exponent, you have to use on both calculators actually the forward arrow to get back down to the main line. Minus 4x squared. And then minus 3x plus 3. Okay, and on this guy, I can go to F6, which is draw. Okay, and it looks like my window. I'm going to go to zoom auto, see what happens. No, I don't like that. This one has some, no, don't like that either. This one has some built-in settings as well. To be honest with you, I'm not as familiar with the built-in settings on a Casio, but I'm just going to make this the negative 10 to 10 for both x and y. And same thing, negative 10 to 10. And then I'll draw that again. Okay, so there we go. On my TI, I can just go zoom standard. And there's the exact same picture. Okay, so I'm going to draw those in and sketch them. So I just want to sort of pay attention. The blue one is fairly straightforward because there's actually like rotational symmetry here. If you rotated the whole thing around 180 degrees, you would see the same thing. So that one's a little easier. I want to pay attention to this. So the min and the max are both on the left side of the y-axis. And then there's the y-intercept, and then it goes down. Okay. So here's the first one. Y equals f of x. And then the second one looks like this. Okay, and if we just go back to the graph again, on either calculator, we can see, actually it's kind of easier to see on the TI. The y-intercept, so the y-intercept of the red one is 3, and the y-intercept of the blue one is 0. So I'm going to just sketch those points in as well. So this over here is 3. And this over here, obviously, is 0. Okay, and then we're just going to try and see if we can pick up a few trends. So for f of x, for the blue graph, what is the value of the constant term? Constant is like the number that's by itself. Yeah. Correct, it's 0, because we're not actually adding a number, right? So you can artificially say y equals x cubed plus 0 if you want, but that is the value of the constant term. Okay? What is the sign of the leading coefficient? Positive, because it's 1, right? What's the end behavior? Yeah. Correct. Starts in Q3, ends in Q1. Okay. What's the domain? Yes. Right. X is an element of the reals. And the range? Right. Yeah, because we have, in this case, unlike yesterday, arrows going both up and down in the vertical direction as well. So here, y is also an element of the real numbers. Okay. And then what about the red graph, g of x? What is the value of the constant term for that function? 3. Okay. Sign of the leading coefficient? Negative. End behavior? 2 to 4. Okay. Domain and range? Yeah. Right. They can both be anything, because if I look at my the horizontal directions of my arrows, they go left and right. And if I look at the vertical direction of my arrows, they go left, up and down. Okay. So let's just summarize this a little bit. Where do you see the constant term in the equation show up in the graph? Yeah. Correct. So the constant term is the y-intercept of the function. Okay. What changes in the graph when we change the sign of the leading coefficient? Yeah, that end behavior, right? Yeah, so not saying sign of the leading coefficient affects end behavior. Right? So if it's positive, it'll always go like this. Quadrant 3 to quadrant 1. And if it's negative, it'll go in the opposite direction. Quadrant 2 to quadrant 4. Okay? And actually, if you just look at the final quadrant, for all of the functions that we've looked at, linear, quadratic, and cubic, when the leading coefficient is positive, they all end in quadrant 1. And when it's negative, they all end in quadrant 4. Okay? Start depends actually if it's something called an even function or an odd function. Even would be the degree is 2, which is quadratic. And odd would be that the degree is an odd number, like 1 or 3. So the linear and the cubic will both sort of start and end on opposite sides of the x-axis, I suppose. So 2 to 4, they kind of go across, or 3 to 1. Whereas the quadratic, which is even, both starts and ends either on the top half of the x-axis or the bottom half. Okay? But the final quadrant is the same for all of them. If it's positive, it ends in quadrant 1. If it's negative, it ends in quadrant 4. Okay? And then also domain and range. What can we say about those? For cubic functions. Yeah. The domain is that x is an element of the real numbers, and the range is that y is an element of the real numbers as well. And of course, just like all the other functions, the only time that we will restrict these is if we have a context in place, right? So I can't actually remember if I mentioned this. Oh no, that's bad. Why do I keep doing that? I didn't do that at all last semester. This semester I've done it like 5 times. Okay, anyway. If we look at, in this course, linear, quadratic, cubic, okay? It just so happens that those tend to be the most common functions for modeling a situation because those actually correlate with the dimensions that we have in this world, right? So linear would be one-dimensional, like anything that's like a line or length. Quadratic is two-dimensional, flat. Flat space is area. And cubic is three-dimensional. We're looking at 3D, so we're looking at volume. Okay? So if, for instance, we're looking at the volume of a cube, right, that would be modeled with a cubic function. Now, in that scenario, it would not make sense to have a negative volume. So that might be a situation where we would limit the range of the function because that would represent the volume. Okay? All right. Now, factored form. So factored form for cubic functions is very, very similar to factored form for quadratic functions in that the coefficient on the outside of all of the factors, this guy, tells you about your end behavior. And then these 3 factors tell us about the x-intercepts of the graph. So one of them in this case would be r, the other one would be s, and the other one would be t. Okay? Now you can, I talked yesterday about having a double x-intercept, so we can have those as well. We'll see what that looks like in a second. In fact, there's one right here. So explain why the function y equals a times x plus r squared times x minus s, where a, r, and s are different whole numbers, could represent the partial graph below. Okay. So when you're answering these, you want to make sure to speak to each piece of the equation and make a clear connection between that piece of the equation and what you see on the graph. Okay? So the other thing that we should pay attention to is this whole numbers, which indicates that A, R, and S should be positive. Okay? Whole numbers start at 0, 0, 1, 2, 3, 4, 5, etc. Okay? Okay. So if we have a coefficient of A, what is that going to tell us about? The end behavior, yeah, right? And because it's whole, that has to be a positive number. So the leading coefficient, A, is positive. And that's consistent with the end behavior that we see in the graph. And the end behavior is quadrant 3 to quadrant 1. Okay, so that connection makes sense. Let's talk about this x plus r squared, the factor of x plus r squared. Okay, so that's should tell us about one of our x-intercepts. Yeah? Not r, almost. But yes, you're right about the twice part. It's not r. If this equals 0, what would x have to be? Negative r, and you're right, it's a double x-intercept. Okay? So there should be a double x-intercept at x equals negative r. And we do see that. We see a negative double 0, or double x-intercept. X-intercepts, by the way, can also be called zeros. So if I say that, then that's why. Okay? And we see that right here, right? Double means that it's just going to touch and not cross through, but just bounce back in the other direction. Okay? So this is negative, and that is a double x-intercept. Okay? And then finally, what about this factor of x minus s? What does that tell us? Yes.
That there's going to be a positive x intercept as well.
Right. Yes. Yes. So there's also an x-intercept at x equals s, and that's positive right there. Okay. I'll put positive and negative in there. And by the way, if you just say it's an x-intercept, we assume it's a single one. Okay? So you don't have to, if you want to write it's a single x-intercept, that's fine, but you don't have to explicitly say that. You only have to explicitly say if it's not single, if it's double or triple or whatever. Yes? Okay, yeah, good question. So where does the negative r come from? The negative r comes from the fact that on the x-intercept, y has to be 0. Because vertically, you're always at 0. So if this guy over here is 0, one of these must be 0, because you're multiplying stuff together to make 0. Okay? So in this point, we're assuming that x plus r equals 0. So you have to think, what value of x would make that 0? It would have to be negative r. Negative r plus r equals 0. Yeah? Okay. Okay, so I want you guys to try this one. And then we'll see how we do, and then we'll go on from there. Where's my pen? Here it is. I'm actually just going to write out the equation again. No, sorry. X minus r, x plus s. Okay, so just about everyone got this piece, right? Leading coefficient positive, end behavior Q3 to Q1. That's good. It's consistent. Everyone got this. This tells us that there's going to be an x-intercept at x equals r, because r minus r is 0, and that's positive, right? So if we kind of connect this up, okay, this is Q3, this is Q1. Here's our positive x-intercept of r. This guy tells us that there's going to be an x-intercept at x equals negative s, because negative s plus s is 0. That's, of course, negative. And so we see that right here. Okay? There's one extra thing, though, that we see in the graph that we still need to connect to the equation. And that is this guy. What's the value of that x-intercept? Yeah. 0. Where does that show up in the equation? Yeah. Yeah. Right? The factor of x means that we're going to have an x-intercept at x equals 0. Because if this factor is 0, I would add a, like a number, times 0 minus r times 0 plus s. If I'm multiplying one of the things as 0, that's still 0. So anytime you just have a factor of the variable itself, that will result in an x-intercept of 0. Okay? All right. So let's talk about a context question. Okay? A motion detector is used to identify the position of a motorcycle during a stunt. The equation y equals 0.32x cubed minus 9.05x squared plus 54.86x plus 200.50 can be used to model the distance of the motorcycle from the motorcycle's detector. The motion detector from the motion detector sensor. The motion detector measures the distance in meters y every x seconds. Okay? So if you can sort of imagine what's going on here, and when I try and do this description, please appreciate that I know next to nothing about motorcycles. I know that they, I think, only have 2 wheels. Some of them have 3.
That's a spider.
What's it called?
Spider.
A spider. Okay. There you go. That's all I know. Okay? But imagine you're like in a stunt. I don't know, there's lots of dirt and stuff. Don't they have dirt in those motorcycle stunts? It's like a park. You know what I'm talking about? Dirt bikes, that's what it's called, a dirt bike. Okay. This is probably like a dirt bike and they're doing stunts and stuff. And they put a machine somewhere in the middle of it and it has a motion sensor on it. And it can tell you at any given time how far the motorcycle is from that sensor as it goes around and does its crazy stuff. Okay, so let's talk about this first. How far is the motorcycle from the motion detector sensor at the beginning of the stunt? Okay, at the beginning of the stunt. How much time has passed? Yeah. Yeah, you're right. It's 200.5 seconds because at the beginning of the stunt, 0 seconds have passed. Which means x equals 0. Okay? So our y value, which gives us our distance, is 0.32 times 0 cubed minus 9.05 times 0 squared plus 54.86 times 0, and then plus 200.5. So of course, everything makes 0 except for the 200.5, which is 200.5. Okay? Where would this show up on the graph? When x is 0. Where are you on? Yeah. The y-intercept, right? This is the y-intercept. And I talked about the y-intercept often being the initial value of the function if one of the variables is time. So this is the initial distance, the motorcycle from the motion detector. Okay? About how long does it take the motorcycle to move 235 meters further away from the sensor? Okay, so let's think about this. We want to move 235 meters further away. So what would our distance be there from the detector if we're 235 meters further than the start? $435.5, yeah. If you're 235 meters further away, you have to add your initial distance not 235. So y is going to be 200.5 plus 235. And that is 435.5 meters. Okay? So one thing I just want to mention is, in question 1, we're given an x value and asked for the y value. In question 2, we're given a y value and we want to know what's the x value that goes along with this y value. Okay? Now, you can do both of these graphically. The second one, though, in this course, you have to do graphically. We do not have the skills at this point to sub in 435.5 for y and solve for x. And in fact, given the coefficients in the function, I don't even think I could do that algebraically. Okay? So we're going to pull out our graphing calculators. And I'm going to go to y equals and clear that out the way. And I'm going to enter in this function. And this function is 0.32. I'm just pulling it up here because I don't want to have to flip back and forth. X cubed. Yes. And then minus 9.05 x squared. Plus 54.86. Whoops. Let's delete that. X. And then plus 200.5. Okay, so if I were to go zoom standard here, I'm not going to see much. That's not really useful. So when you are setting your window settings, you need to remember, what do these variables represent? Okay? X is time in seconds that this stunt is taking place. How long do you guys want to track this for? Yep. 25 seconds? Okay, sounds good to me. So the minimum time would be 0. You can't have less than 0 seconds. And let's track it for 25 seconds to start and see where we get. Okay. Now, let's think about the y values. Y value is the distance in meters that the motorcycle is from the sensor. What's the smallest distance that could be? Okay, well, that would be the smallest. 0 is the smallest. 435.5 is what we're interested in right now. Could it actually go further than that, though? Sure. So let's maybe track it up to, like, I don't know, 1,000. Okay, 500 is better. Okay, well, listen, we could play around with this. I'm going to make the scale 100 just so that every little tick represents 100. That's not so important, though. And there we go. Actually, that's quite nice. I like that. Okay, so this is the first 25 seconds of this journey. Okay, and if I were to show how I came up with my answer here, I would want to make a little window. Right, I'm not going to copy that out right now, but I would also put the window settings in. So my x min was 0, my x max was 25, my x scale was 1, my y min was 0, my y max was 1,000, and my y scale was 100. Okay, and then this looks like this. All right, so it kind of goes like that. Okay. Now, what I'm really interested in right now is when y is 435, what is x? Okay. Y equaling 435 is somewhere around here. 435.5. If we knew the x value, we could just plug it into the equation. Getting the y value is a little bit more challenging, though. So what we're going to do is actually graph another function. And that other function is going to be y equals 435.5. That's the horizontal line at 435.5. When we do that, we can look for an intersection point. And what we're interested in is, what is this? What time does that happen? Okay, so that's going to kind of be our process. So one of the equations, by the way, is 435.5. The other one is the original equation from the question. I'm being super lazy here. Technically, you should write that out. Okay, so I am going to do that below. And there it is. Now, to get my intersection, don't use the trace button. Go to that second calc menu and go to number 5 for intersect. And it's going to ask you to get close to the intersection point on the first curve. So that's close enough. I'm going to hit enter. On the second curve, that's close enough. I'll hit enter. And then do I want to guess? Yes, I do. And so we can see that that happens to the nearest hundred at 22.01 seconds. Okay, so this is the point, 22.01, 435.5. And so if we want to know when does this happen, we would say, oh, to the nearest second. Okay, so to the nearest second, we can just say at 22 seconds. Okay, now on the Casio, this process is even simpler. After you enter in your function, where is it? Oh, menu. Enter. There we go. Okay, so what was it? It was 0.32x cubed. And then minus 9.05 x squared plus 54.86 x plus 200.5. Okay, and then I'm going to delete this. Okay, and then I'm going to go to the window, and I'll do the same setting. So this was 0 to 25. Whoops, sorry. I'll do that again. And then my y min was 0, and my y max was 1,000. And this was 100. Perfect. Okay, and then I'm going to draw, and there it is. Okay, now on these calculators, you actually don't have to draw another line. You can just go ahead and go to gsolve, and then go here. And you want to figure out an x value, an x calculation. You know the y value, you want the x value. So you're going to hit F2, and you enter in y equals 435.5. And it will give you that x value of 22.01. Okay, we don't have that feature on a TI, so on a TI you always have to graph a horizontal line. Okay. Lastly, what is the domain and range within the context of this question? So let's start with the domain. Domain is time in seconds. What makes sense for time here? What's the minimum time that this stunt could last? 0 seconds. What's the maximum time? Not 25, because I just picked that arbitrarily. Is there a maximum time here? No. So actually the domain is just x is greater than or equal to the real number. greater than or equal to 0. That would make sense, greater than or equal to 0, they're real numbers. And then for the range, if you're thinking about y being a distance, it kind of makes sense that y should be greater than or equal to 0. But if you look at the graph, we actually don't see any distances go below this point. That's the minimum distance. So we actually have to find that point to be able to determine the range. Okay, so on our TI, we're going to go again second calc. And this is a minimum value. Okay, so I'm going to go to the left. Here's the left side. Then I'm going to go to the right. And the minimum distance remember is y, happens at about 67.1 meters. And this is 15.1. But in this case, we're not interested so much in what the time is. What was it, 67.1? We're interested in what that distance is, because that's the smallest distance the motorcycle ever gets to the motion detector. Again, on the Casio, if that's what you're using, you would go to GSolve again, and then you're looking for the minimum. And it just tells you the point. There it is, 67. It's hard to see because it's kind of covering the X. If you have that problem though, just change the window setting a little bit and make Y go into the negatives, and then this cursor will move up a little bit and you'll be able to see that number. Okay. All right, so there's the domain and range. Okay, that's a tricky question. It's a harder question because number one, that range piece is kind of tricky. And number two, it's just not an application that's that easy to picture in your head, right? If you're thinking about volume, you can imagine, okay, 3 side lengths. That's where we get the x cubed from, right? But this one's a little bit trickier to imagine. Okay, so I'm going to skip these for now. I'm going to get you guys to do these for homework. What I do want to talk about, though, is now that we've kind of learned everything, we're going to talk about some trickier questions. And those are typically when you are given a description of what's happening, but you're not actually given an equation, you don't have a table of values, you don't have a graph. It's usually a description in words. Okay? So the best way to be able to answer these types of questions is try and imagine the situation, try and draw it, and then put axes into your drawing. Okay? So for example, Jeff is standing on a bridge 5 meters above a river. He picks up a small rock and tosses it in the air. The rock reaches a maximum height of 12 meters in 1 second and hits the water in about 2.3 seconds. Okay? So if we imagine what's going on, we got Jeff, he's standing on a bridge. So again, I'm not really good at drawing, but here's the bridge, let's say. Here's Jeff. This is water. And how tall is the bridge again? 5. So this is, we're going to assume that his height is not important here. 5 meters. Okay? And he takes a rock and he throws it in the air. What is that path going to look like? Yeah, parabola, right? So here's the rock, and the rock goes into the air, and then it lands. Okay, so that's the path. Now I'm going to actually put axes on top of that. So where do you think it would make sense to put my origin, the point 0, 0? Yeah. Well, at 5 meters, you're 5 meters above. I would put it here. That's the height of 0, and time is 0 when it starts. So I'm just going to do this. And let's see now if we can fill in some information. So we know that this over here is 5. Okay. It reaches a maximum height of 12. So this over here should be 12. Okay? When does that happen? Yeah, after 1 second. So this down here is 1. And we also know that the rock reaches the ground, it hits the water in 2.3 seconds. So this over here is 2.3. Okay? So the first question is determine when the rock reaches a height equal to the bridge, but on the way down. So when is the height of the rock equal to this, but on the descent? What do you think that time would be? 2, yeah. We have to use symmetry here, right? Parabolas are symmetrical about the vertex. So this is 2 seconds. Okay? And then determine the domain and range within the context of the question. Okay, what is the minimum height? Or let's start with domain rather. What's the minimum time? 0, right. And our x value is time, or our independent value, I should say, is time. What's the maximum time? 2.3. So we have this double inequality going. It's going to look like that. Okay? And then let's talk about our height. What's the minimum height? What's the maximum height? 0 and 12, right. Okay? Questions with that so far? Okay. I think I do want to do this one as well. Let me just see here. Yeah. Okay, I want to do this question as well. Hopefully we'll have time, at least to start it. And then I'm going to leave it there for today. Okay? So, company wants to change the dimensions of a particular box, which will increase the volume. The box is currently 5 centimeters by 4 centimeters by 12 centimeters. To create a new box, the company will increase each dimension by the same amount. The volume of a box can be calculated using the formula V equals L times W times H, length times width times height. The company does not want the volume of the box to exceed 1,000 centimeters cubed. Determine the largest amount by which each dimension of the box can be increased to the nearest tenth of a centimeter. Okay. What do you think would be a valuable thing to do right now? Simple. Yeah. Even before making an equation. Yeah. Draw a box. Yeah. I would draw the original. Okay, so this is the original. It is 5 by 4 by 12. We are increasing each side by the exact same amount. Do we know what that amount is? No, so let's make that the variable. Let the length of the increase be x. Okay. Well, currently, the length is 5. If I increase that by x, what's the new length going to be? Right. 5 plus x or x plus 5? What will the new width be? 4 plus x. And what will the new height be? Right. Okay. Now we have this volume formula. That volume is length times width times height. And we have an expression for the length, width, and height, all in terms of x. So to get an equation to model this situation, we're just going to sub in those expressions for each variable. So our length was 5 plus x. Our width was 4 plus x. And our height is 12 plus x. Okay. Now that we have an equation, you guys can go ahead and solve this graphically. So I'm going to leave it there for today. I want you guys to try and work on this for the rest of class, okay? Now, for homework though, there is a bunch of questions in your booklet from page 23 to 28. There's also some textbook stuff. A lot of people, when I have practice questions in the booklet, like working out of that. So you can do that if you want. I'm giving you lots of options, but the important thing is that you do something every day, right? I'm just going to stop the recording because I don't need this to be in the video.